Hello everyone, and in this video we have an A2 EDEXCEL question on moments. So let's have a look at this question. So it says a plank AB has a length of 4 meters and a mass of 6 kilograms. The plank rests in a horizontal position on two supports, one end at B and the other at C, where AC is 1.5 meters. A load of mass 15 kilograms is placed on the plank at the point X as shown in figure 2. The plank remains in horizontal equilibrium, and it remains horizontal and is in equilibrium. The plank is modelled as a uniform rod and a load is modelled as a particle. The magnitude of the reaction on the plank at C is twice the magnitude of the reaction at B. Find the magnitude of the reaction on the plank at C. So the first thing I would note is here's a sketch representing the situation. The first point at which students sometimes get confused is knowing where to put the mass. And you'll notice that in the question, they tell us the first thing to look out for is that it is a uniform rod. Okay, you see over here in the question, they're saying a uniform rod. Now, the significance of that is that the mass is acting at the center. And the plank has a length of 4 meters. So therefore, it's going to be acting 2 meters away from one of the ends. So 1.5 add 0.5, that's how we know that it's acting from there. That's the first thing. The second thing, when they tell you that the reaction at one of the points is double the reaction at the other, so in this case, we've got the reaction here is twice the reaction here, then you only need to model it in terms of one unknown, because you just call that one R and this one you call 2R. Okay, so instead of saying reaction at C and reaction at B, you think of it as one unknown. So when they tell you that piece of information, it effectively kind of reduces the number of unknowns in the question by 1. So part A, so that's how we've set the sketch up. So let's get straight into it. Part A, we've now got to find the reaction on the reaction at C. Okay, so we want to find this force here. So I think we should just resolve vertically in this case. So if we're going to resolve vertically, we have 2R plus R. So that one and that one, the force is going up, equal the force is going down. And the forces going down are 6G add 15G. So we've got, therefore, 3 times the reaction force is equal to 6G add 15G. And from that, we can work out what that reaction force is. So let's just do that. So we're going to say 6 add 15 is 21 times by 9.8. And then we're going to divide that by 3. And that gives us 68. That gives us 68.6. Okay, so 68.6 is that reaction force there. So 6G, 15G, and we've got 2T there, yeah. Okay, now that's the reaction force R, but the question is asking us to find what the reaction force is here. So we need to say 2 times R is equal to 68.6 times by 2. So we times that by 2, and that gives us 137. So the force, the reaction force at C equals 137.2 newtons to 1 decimal place. Okay, that's fine. So that's our answer to part A. Next bit, find the distance AX. Okay, now the problem we've got here is we don't know where this package or parcel or whatever it is put. Okay, so a load. So we don't know where that is. Now what I'm going to do is I'm going to basically call the distance of the object. I'm going to call that distance X. Okay, and now we know what R is. If I now take moments, you're always going to be careful about where you take moments about. If I take moments about C here, then that's going to be really useful to me because I'm going to have, I know what R is, I know everything else. The only thing I don't know then would be the X. So I'm going to choose to take moments about C. So it's in equilibrium, so the sum of the clockwise moments is going to equal the sum of the anti-clockwise moments. So let's think about our clockwise moments. So we've got X, the distance of the object from C, times by 15G. That's our clockwise moment. We've also got a clockwise moment here from the center of mass of 0.5. times by 6g. So there are clockwise moments, and that equals our anti-clockwise moments, which is r times by the distance here, which is going to be the length of the rod minus the distance that that is in, which is going to be 2.5 meters. 2.5 times r, because the whole rod has a length of 4, and that's 1.5. So the distance from here to here is therefore 2.5. We know what r is. We know that r was 68.6. So we've got 68, let's just double check that, 68.6, yes, times by 2.5. And then we can basically subtract from that 0.5 times 6g, which is going to be 3g. And then we divide by 15g. So all we're doing here now is just rearranging this equation to make x a subject. Okay, so without any further ado, let's work that out. So that is 68.6 times by 2.5 minus 3 times by 9.8. And that whole thing is over 15 times by 9.8. And that gives us 0.96. So that gives us x is equal to, well, let's have a look what that is. That's actually 29/30. And we want to know the distance. What's the question asking? The distance from A to X. So we've got to add on 1.5. So therefore A to X is equal to 1.5 plus 29/30. So A to X is equal to, plus 1.5, gives us 2.46. So actually that is 27/15. So 37/15 rather, 37/15, which we can say is 2.47 meters. 3 significant figures. So we've now done our part B. So we basically just took moments about C, and that was quite nice. So far so good. So we're now 8 marks into this moments exam question. Right, now let's see what happens. So the next bit, the load, this load here, X, is now moved along the plank to a point Y that is between A and C. So this load is moved along here. So it's now over here, somewhere, we don't know where. Let's call it 15G, there it is. And it's been removed from here, so it's gone from there. And it is now moved along here. Okay, so that's our new situation now. We're going to find, so it says this is the interesting bit. It says, given that the plank is now on the point of tipping about C. So when something's on the point of tipping, I'm going to call this distance here X for this calculation. It's on the point of tipping about C. Now, what that means is it's about to go like that. It's about to tip up like that, okay? So the significance of that is if something's on the point of tipping, this reaction force here disappears. And in fact, you could even remove that support altogether and it would make no difference to the situation, okay? Because it's on the point of rotating or tipping about the point C. So it makes sense for us now to take moments about C. So let's take moments about C and see what happens. We're still in equilibrium, so the sum of our clockwise moments equals the sum of our anti-clockwise turning moments. And let's see what we've got for the sum of our clockwise turning moments. So we have got 0.5 times by 6g. So that's our clockwise moment. We haven't got that x anymore, that's from the previous bit. And then let's have a look and see what we've got for our anti-clockwise turning moments. Our anti-clockwise turning moment is just given actually by the 15g, the mass of the object, times by its distance away from C. That's quite nice actually. So therefore x is equal to 0.5 times by 6g over 15g. And let's see what that gives us. So that gives us 0.5 times by 6 times by 9.8 over 15 times by 9.8, and that gives us 0.2. So that is 0.2 meters. And the question is, find the distance from A to Y. Okay, so we found that that distance is 0.2, A to Y is 1.5. So therefore, A to C is 1.5, and they're calling this is the point Y where it's attached. So therefore a to y is equal to our 1.5 meters, take away 0.2. So a to y is 1.3 meters. And that is the answer to part C. I hope that you found that useful. That's just an introductory exam question for you there. I think about 12-mark question on moments. I'll see you in the next video.